once again, I'm posting a video here for the homework questions from yesterday's work. These are from the intersection of lines and intersection of planes, which was day 6 and 7 on your Unit 3 outline. Just because there was quite a few questions asked and I didn't want to take up such a big chunk of our class time working through these. I thought this way you will each be able to kind of check on the questions that you needed the most help on. So first one here is question 7 on page 496. For the following, determine points of intersection between the line and the plane, if any exist. So for A, we would remember we always want to have our line equation in parametric form. So x would equal -1 plus 6p, y is equal to 3 plus p, and z equals 4 minus 2p. And then we're going to have the plane, which is going to be in Cartesian form. X plus 2y minus z plus 29 equals 0. And I'm going to substitute in each of the parametric equations for x, y, and z and solve for that p value. So I'll just kind of mark those off there. So here I have -1 plus 6p plus 2 times 3 plus p minus 4 minus 2p plus 29 equals 0. Squeeze that in down there. And then I get -1 plus 6p plus 6 plus 2p minus 4 plus 2p plus 29 equals 0. So if I kind of collect like terms here, my p's, I've got 6, 2, and 2. So I have 10p, and then 29 minus 4 is 25, plus 6 is 31, minus 1 is 30, equals 0, so p would equal -3. So if you get a value for p, that means that it's a situation where there's one point of intersection of the line and the plane, and then we'll just substitute that back in for the parametric equations for x, y, and z to find the actual point. So -1 plus 6 times -3, -1 minus 18, my x is -19, and then the y is 3 plus -3, so y is 0, and the z is 4 minus 2 times -3, so z is 10. So the point of intersection of the line and the plane is -19, 0, 10. So kind of similar for B, except that we need to rewrite x, y, and z from the symmetric form of the equation of those lines into parametric. So remember, in the symmetric we have each of those pieces of the symmetric equation would be equal to our t value, or whatever variable you want, I suppose, but I'll just do t. So then for the x, I get +1 plus 4t when I isolate that. And then the y piece, I have y plus 2 over -1 equals t. And rearranging that equation, I get y equals -2 minus t. So there's my parametric equation for my y value. And the z, it was just z minus 3 equals t. So that would come up to z equals 3 plus t. So now I have 3 equations, one for x, y, and z, and I'll substitute that into the Cartesian equation of the plane. So those are my parametric form for my line. The Cartesian equation for the plane is 2x plus 7y plus z plus 15 equals 0. So I'm going to substitute in the parametric equations for x, y, and z and solve that for t, if I can. So here I've got 2 plus 8t minus 14 minus 7t plus 3 plus t plus 15 equals 0. And when I collect like terms, I get 2t. And then looking at the number parts, 2 minus 14 is negative 12. Negative 12 plus 3 is negative 9. And negative 9 plus 15 is 6. So 2t plus 6 equals 0. So t would equal negative 3. So that gives me, oh, that's weird that they were both, the parameters were both negative 3 in part A and B. Then I'm going to sub those in to the parametric forms of the equations of the line up there. So x equals 1 plus 4 times, negative 3. So x equals negative 11. Y equals negative 2 minus negative 3. So y equals 1. And z equals 3 plus negative 3, so z equals 0. So the point of intersection here is negative 11, 1, and 0. So the next one, I don't really like the method of showing that two lines are coincident. I feel like this is a lot longer, the solution in A, but I'll do this both ways. So this says, show that these lines are coincident by writing each line in parametric form and comparing components. So really here, we would notice right away that the two direction vectors are equal. And remember, they can be either equal or scalar multiples of each other, so that would show that the lines were collinear. So we basically want to see, are these lines parallel or are they coincident? Is it like two lines exactly the same? That's what we're trying to figure out. We know that they're not going to intersect at one point because they have the same direction vector or a scalar multiple of the direction vector. So the first way is to, and this is the one that I don't really use, but I will show you what they mean for sure, is to write these in parametric form. So L1, we would have x is negative 2 plus 7s, y is 3 minus 2s, and z is 4 plus 2s. And for L2, doing the same thing, we've got x is negative 30 plus 7t, y is 11 minus 2t, and z is negative 4 plus 2t. So if we compare components, we're kind of going to come up with equations for using s and t and see if it's the same relationship here. So I could come up with an equation from the x's. I would say negative 2 plus 7s equals negative 30 plus 7t. And depending how you wanted to look at this, I might say 7s minus 7t equals, bringing the 2 to the other side, it would be negative 28. And then divide 7 out by each term, I get s minus t equals 28. Or s equals t plus 28. We kind of want to see a relationship between the s and the t. And I feel like this is longer, so I don't do it. But typically. And then we do the same for the y's. And the same for the z's. So here for the y's, I would do 3 minus 2s equals 11 minus 2t. And maybe I'll get each one in terms of, say, like an s equals. So negative 2s equals negative 2t, and bringing that over, we'd have plus 8, and divide out So S is t minus 4. Then we would do a substitution with these two so we could figure out what the value of t was. So here we could say t plus 28 equals t minus 4, and we would get, we are going to, oops. Sorry folks, just found my mistake. I got myself in too deep here and missed dividing this one term here by 7. So that's my problem. I got to something that did not work. I forgot to divide the negative 28. So S equals t minus 4. And then that would be the same that we got from the second one. So we can compare and say that that's the same relationship. And then similarly, the third one, we're going to get the same thing. I was like, ooh, I thought I was supposed to get that same thing, and all of a sudden I didn't. But we're okay. So using the z's, I get 4 plus 2s equals negative 4 plus 2t, and same kind of idea here, 2s equals 2t minus 8. When I bring that the 4 from the left side over there and subtract it, and then dividing out, I get s equals t minus 4. So I have the same relationship between my two parameters where these intersect, or where they would be the same line, because there's the same relationship between the parameters in each case. Now, I find that that's more complicated than you need to be. When I'm looking at two lines that I know are parallel, if I want to know if they're coincident, the way I look at this, and I'm just going to kind of erase this and show it in a bit more detail. If I have one line and another line, and I know for sure that their direction vectors are scalar multiples, I know that there's a point and a direction vector on each line. Right? I've got this point and that direction vector. So basically what I like to do, and I prefer this method for B, I'm going to check, is the point from line 1 on line 2? And if it is, if you know, hey, this point on the red line is also on the blue line, it's on here somewhere, and the red line and the blue line are parallel, then you know that they have to be the same line. So what I would do is I would check, is the point from the first line, negative 2, 3, 4, on L2. And to do that, I'm just going to look at the parametric equations of L2, so y equals 11 minus 2t, and z equals negative 4 plus 2t, way squeezed in there, a little bit running out of space. And I'm just going to sub in x, y, and z from the point and solve for t in each. So negative 2 equals negative 30 plus 7t. Positive 28, when I bring that over, equals 7t, so t equals 7. And then doing the same here, if y is 3, 11 minus 2t, so bring that over, negative 8 equals negative 2t, and t equals, what am I doing? Having trouble dividing today. T is 4 for both. And the last one, 4 equals negative 4 plus 2t. So then 8 equals 2t, and divide that out, t equals 4. So we get the same parameter for x, y, and z. So therefore, the lines are coincident because they are parallel and the point from line 1 is also on line 2. Now, they have to be parallel for that to work, because you could have intersecting lines that just happen to intersect at the position vector or the point given for one of the lines. But if you know that they're parallel and one point from this line is on the second line, then you know that they have to be the exact same lines. And the next one, show that these, same one, I actually forgot. I anticipated running out of space and had another slide to do all that work on, but I ended up being able to squeeze it in. So I'm going to stop there and do the rest of the questions that I've put on a different Jamboard in the second video.